So in this video, we're going to be talking about properties of real numbers. This is the last section in chapter 1, and it's really finishing off all this intro stuff, right? And so these properties of real numbers, I'm just jumping right in. We're going to start with the commutative property. And there's one for addition as well as one for multiplication, not one for subtraction or division, and I'll kind of get into that. Now, these properties that we're going to talk about, all of these, are really things that you're going to want to intuitively know very quickly, because you're going to be using them all over the place. And I think most of them will be pretty easy to understand and kind of intuitive. We already know this. So let's just get started with the commutative property of addition. So I've written these all out beforehand so that we can kind of move a little quicker. The commutative property of addition states that if a and b are real numbers, a plus b is equal to b plus a. So we can kind of see this in super obvious examples. So like 2 plus 3, right? That's 5. What if we switched it around? What if we made it 3 plus 2? Well, that doesn't change anything, right? That equals 5 still, right? It doesn't matter what order we put these numbers in when we add them, they're still going to make the same result. And so that's all the commutative property tells us. It tells us that the order doesn't matter. The order of the numbers when we're adding doesn't matter. Now, it does matter when we're subtracting, right? So if I say 2 minus 3, right, that's negative 1. But if I say 3 minus 2, that's a positive 1. So you actually can't say about subtraction that the order doesn't matter, because the order does matter when you're subtracting, which is why we only have a commutative property of addition, not subtraction. So so now we're going to move to the commutative property of multiplication. And it basically says the same thing, same exact thing as addition, except for we're multiplying instead of adding, right? So it says if a and b are real numbers, all of these properties are going to assume that these are real numbers because these are properties of real numbers, right? So if a and b are real numbers, then a times b is equal to b times a. And we can demonstrate this again with our 2's and 3's, right? So 2 times 3, if you think about that as adding 2 3 times, right? 2 plus 2 plus 2, then that's going to be 6, right? If we do 3 times 2, that's going to be 3 plus 3, right? 2 3's. And that's still going to be 6. And it turns out that is the case for all pairs of numbers that you're multiplying. It doesn't matter what order you put them in. 4 times 2 is 8. 2 times 4 is also 8. And these are probably things that you're already doing all the time, but it's just kind of, in math, we have to kind of prove everything, right? And so we have all these properties that tell us we're allowed to do that. Okay, the associative property of addition, and I know I'm moving through these really quick, but I have them all written down. You can, write them down yourself, and if you need to. But I kind of think that everyone kind of already has an intuitive sense of a lot of these. Okay, the associative property of addition. So what this tells us is if a, b, and c are all real numbers, then a plus b, in parentheses, plus c, is going to be equal to a plus b plus c, in parentheses. And really, the simple idea that this is telling us is that the commutative property told us that the order doesn't matter. The associative property tells us that the grouping doesn't matter either, right? Or the associations, you could think of it as. So let's just do this with 2's, 3's, and 4's, right? So if we put 2 for A, 3 for B, and a 4 for C, what's that equal to? Well, the 2 plus 3 is 5, right? PEMDAS, we start with the stuff in parentheses. And then 5 plus 4 is 9. Okay, what if we changed it so that it looked more like this form, where we have sorry, I'm already not doing that. 2 plus 3 plus 4, right? Well, that's going to be 3 plus 4 is 7, and then 7 plus 2 is 9. So, we can, the fact that I can write it like this doesn't necessarily prove it, but you can kind of see how it's just going to always turn out that way, right? You can always rewrite with addition these kinds of things. Oh, I do want to mention, like, again, this does not work with subtraction. If we take, let me get an example for subtraction here. Yeah, okay. If we take 10 minus 3 in parentheses minus 2, right? Well, 10 minus 3 is 7, and we're still subtracting 2. And 7 minus 2 is 5, right? If we instead did it 10 minus 3 minus 2, well, that's the same as, well, 3 minus 2 is 1, so that's 10 minus 1, which is 9, which is not equal to 5, right? So it does not work with subtraction, just like the commutative property does not work with subtraction. And you'll see the associative property of multiplication doesn't work with division either, just like the commutative property of multiplication doesn't work with division. So the associative property of multiplication, actually, let me just restate what basically the associative property of addition is. The grouping of numbers being added does not matter, okay? I'm just putting that out there. Okay. With the associative property of multiplication, it's saying the exact same thing, but we're multiplying, right? It's just saying the grouping and multiplication doesn't matter. So if I have over here 2 times 3 times 4, right? 2 times 3 is 6, 6 times 4 is 24. If I have 2 times 3 times 4, 3 times 4 is 12, 2 times 12 is 24. It's always going to work out that way with multiplication. With division, the order and the grouping does matter, right? And the associative and commutative properties for both addition and multiplication are kind of a similar idea, right? Which is that the order in which you do things kind of doesn't matter when you're adding and multiplying, right? Because it's like you're combining a bunch of numbers into one, and it doesn't matter what order you put them in, right? With subtracting and dividing, it matters because one number has to do something to the other number, right? It's not like they're both collaborating to become one thing. It's like, okay, you're taking this much away from one number or something like that, right? So that's why it doesn't work with subtraction and division. But we have these properties, commutative and associative, for addition and multiplication. Those are important. You probably are pretty comfortable with using them already. So now we're going to move on to the next one. This is the identity property of addition, and we also have one for multiplication. So what this says is that for any real number a plus 0 is equal to a, right? Basically what that means is that adding 0 doesn't do anything, right? 2 plus 0 is still going to be 2, right? And it turns out that these rules, or this rule here, actually does work with subtraction also. So you could kind of copy and paste that into the identity property of subtraction, right? Where a minus 0 is equal to a, because, 2 minus 0, that's still going to be 2, right? And so because of this, we're actually going to learn a new word here. This means that 0 is what we call the additive identity. Which all that means is that when you add it to something, it doesn't do anything. Which, kind of sounds like not a very special thing to get an award for, but 0 does. So when you add a number, add 0 to a number, it doesn't change the number at all. When you subtract it, same thing, doesn't do anything. And we have one for multiplication as well, but it's not 0, right? With multiplication, it's going to be 1, right, is our magic number. So if I say 2 times 1, that's still going to be 2, right? Multiplying by 1 doesn't do anything, basically. So let's and then division is the same way, right? 2 divided by 1. Again, every time you divide by 1, it's not doing anything at all. It's still 2. And so because of that, we have another name for, and this time 1 is getting a name. 1 is I should have done this in like blue or something, but anyways, the multiplicative, I'm already writing this wrong. It's a complicated word, you know. Multiplicative identity. Sorry, not inverse. We're getting to that in a second. The multiplicative identity. And again, it means the exact same thing. It means that whenever you multiply it, it doesn't change anything. Now, we have, along with properties for things that don't change anything, we have properties that are about canceling numbers, kind of, right? So this is the inverse property of addition. And really, the additive inverse of a number, I'll get to that word in a second, is really just the number that you can add to the number that will get you to the identity, the additive identity, right? Or 0. So the inverse property of addition says that for any real number a plus negative a is going to equal 0. In other words, any number plus its negative is going to kind of cancel, they're going to cancel each other out and become 0, which then if we add something, it's going to do nothing, right? So if I have 2 and I add a negative 2, right, that's, those 2's are going to cancel each other out, and so we're going to get 0. And that is only for addition. For subtraction, it's kind of, obviously 2, if you want to get to 0, that'll be 2 minus just 2, right? And really that's the same as adding, because that can be the same as 2 plus negative 2, right? We're doing the same thing either way. So because we have this property for negative numbers, right? And that's actually part of how negative numbers are sort of defined, right? It's the opposite of the number, because when you add it to the number, it equals 0. So because of that, we call negative a the additive inverse. Now, most of the time, you're not really going to be worried about these terms, but it's good to know them. Additive inverse, additive identity, and then we'll have the multiplicative ones too. Again, being an additive inverse just means that when you add it to the number, it equals 0. So similarly, we have one for multiplication. This states that a times 1 over a is equal to 1. In other words, we have 2, right, again. If we multiply by 1 over 2, that will equal 1. And I just want you to notice for a second, if you remember we talked about, I think this was 1.3 fractions. This 1 over 2 here, or this 1 over a, you could look at, I guess, that is the reciprocal of the number, right? We had that name for it, reciprocal. So it turns out the reciprocal of a number is the multiplicative inverse of that number. And all that means is that when you multiply it, it'll equal 1, right? So if you take the reciprocal of 4, which is 1 over 4, you're going to get 1. And you can kind of think of it like they're canceling each other out, right? So these 2's canceled each other. These other 2's canceled each other. Why? Because you're doing a multiplication here, and then you're dividing here, right? It's, that's probably a confusing way of putting it. It's basically like you're saying, how many times does 4 go into 4, right? Because remember, multiplying by the reciprocal is the same as dividing, right? Or dividing is the same as multiplying by the reciprocal. So this, saying, 5 times 1 over 5, right? That's exactly the same as saying 5 divided by 5. And if you think about how many times does 5 go into 5, well, that's going to be 1. How many times does anything go in itself? It's always going to be 1. And that's precisely because 1 is the identity, the multiplicative identity, right? So basically the inverse property of multiplication just tells us that anything times 1 over that thing is going to equal 1. Or, in other words, anything divided by itself is 1. Okay. And so because of that, 1 over a, we call that the multiplicative inverse, right? Which is a really long word. But again, that just means when you multiply these two numbers, they become 1, which is the multiplicative identity, right? Moving on to properties of 0. 0 is a really cool number. So actually 0 and 1 are both some of my favorite numbers in all of math because they have all these special things about them, right? And especially 0. 0 is like the anti-infinity. So it has some things in common with infinity, actually, but kind of backwards, right? Because it's nothingness, right? It's like a black hole. So, properties of 0. The first one is for any real a times 0 is equal to 0. These properties of 0 are really just a bunch of things that we have about 0 that are special about 0, right? So it turns out that any number, a, when you multiply by 0, you're going to get 0, right? So if we have 2 times 0, that equals 0. Basically, 0 trumps any number. You could have 1 million, but if you multiply by 0, you're still going to get 0, right? So 0 is really good at making nothing out of something, right? Okay, also, for any real a that is not equal to 0, and it's not equal to 0 because of the next property that we're going to talk about right after this, but for any real a that is not equal to 0, 0 divided by a is always going to equal 0, right? Why? Well, how many times does a go into 0? Like, what do I have to multiply a by to get to 0? Well, like we just talked about over here, you multiply by 0 to get to 0. So that means that a divided by 0 is always going to equal 0. So really, this is just kind of naturally stemming from that first property of 0, right? So any number dividing into 0, not divided by 0, dividing into 0. So for example, 0 divided by 2, it's always going to equal 0. Whenever 0 is in the numerator of a fraction, it's going to equal 0. Unless 0 is in the denominator of the fraction as well, which is related to this next idea. The final property of 0 that we have is that for any real a divided by 0 is undefined, okay? And what that means is that it just can't exist, right? It just doesn't exist. A divided by 0, so let's take, 2 divided by 0. This is, again, with division, we're asking how many times does it take 0, how many times can 0 go into 2, right? Well, it can just keep on going. It's never going to get to 2, no matter what. So that's why it's undefined. And so one thing that's interesting, and this is why in this in that second property of 0, it mentioned a has to not equal 0. Imagine if we had 0 divided by 0, right? Well, now this is kind of confusing because we know 0 divided by any a should equal 0, right? Except when a is not equal to 0. So it turns out 0 divided by 0 is undefined. It's really confusing when you try to think, like, how many times does 0 go into 0? Well, it could be 1, right? Because we know any number over itself is supposed to equal 1. But really, it turns out this number is sort of the master rule when you're dividing by 0, okay? So even when you have 0 over 0, and it looks like maybe it could be 1 or it could be 0, it's undefined. So just keep that in mind. All right. So that's how 0 was special. Now I'm just going to finish this off with one last property, and this is maybe the one that I would want you to pay the most attention to, because it is so important when we're working with algebraic things, and it has some tricky things that can happen here. So if we have, it says, okay, if a, b, and c are real numbers, then a times b plus c is going to equal a times b plus a times c. A lot of the ways, oh, and it also means, same thing with subtraction, right? I just wrote the same thing but with a minus sign. One way to look at this is basically like this is being distributed, right? That's we call it the distributive property. We put these arrows, right? We multiply times every single term in this parentheses, in these parentheses. So this becomes a times b, right? The arrow there, and then we put another arrow to c, right? Plus a times c. And this could have more than b and c, right? This could be like a times b plus c minus d plus e. That would become a times b, right? We just make all these arrows to every single term in the parentheses here. So that'd be ab plus ac minus ad, and then plus ae. So let's see this in action, right? So if I have 2 times 3 plus 4, right? If we just think about it and we just evaluate it ourselves in our minds, 3 plus 4 is 7, 2 times 7 is 14. So we know it should equal 14. But what if we use the distributive property instead of kind of just evaluating it first? Well, we distribute this 2 into here, right, to each of these numbers. So 2 times 3 plus, that's that AB, plus 2 times 4, which is that AC. 2 times 3 is 6, and 2 times 4 is 8, and 8 plus 6, sure enough, is 14. So that's kind of how that works in real life, and this is going to be really helpful when, we come into situations where we have variables in this parentheses, so like x plus 4 times 2, right? We can't actually evaluate x plus 4 because we don't know what x is, but we can simplify this by multiplying that 2 in. So we say 2x plus 2 times 4 is 8, right? We distributed that 2 in there. Okay, and so the thing that I really want to highlight right now about the distributive property is how it works when you have a negative sign in front. Because this is going to come up all the time, and it is a very, very common mistake in algebra. So if we have something like negative 11 times 4 minus 3a, and we want to use the distributive property like this to, put that in there, we have to keep this negative sign here also. And what that means, if we do it kind of using parentheses, it'll be very clear. We take negative 11 times 4, and then this minus in here also has to stay, and that is on the 3, right? So you can think of this as being the same as negative 11 times 4 plus negative 3a, right? Because that's how subtraction works. It's the adding of the negative. So if you think about it like that, you realize that that negative has to stay with that 3. But you can, so basically this is going to be the same as plus negative 11 times negative 3, right? And that's the trickiest part, I think, about this. Or okay, if you look at how we put it here, right? We took that negative and we just kind of kept it along there. So let's say we want it to stay a subtraction, right? For whatever reason. So negative 11 times 4 here, right? Then when we go to the 3a, we take the minus sign from the 3 right there. We're multiplying by negative 11. And then the 3 doesn't have a negative now because we already put it out in front here. Okay, so either way, you can see these two negative signs are going to cancel each other. And so it's actually going to turn out to be the same as, okay, negative 11 times 4 is negative 44, plus 11 times 3, which is 33, right? Because those negative signs canceled. And so this is going to equal negative 11. So always, it's really tricky, that negative sign, especially when you're distributing a negative sign into a subtraction. Also, if you had like, okay, 4 minus 2 times 3 minus 8, right? This is really tricky. So you don't always realize that this out here is actually a negative sign in front of the 2, right? Now, you can sort of separate it from that, right? You can put parentheses around this if you like. It's either you have to distribute that negative sign into that distributive property equation, right? Or you have to keep the parentheses around it when you're finished. What I mean by that is, what a lot of people might do here is say, okay, that's going to be equal to 4 minus 2 times 3, right? So we distribute the 2 in, 2 times 3 is 6, and then minus 2 times 8 is 16, right? Like that. That's what a lot of people would do here, but that is not correct. And the reason for that is because this negative sign is going to change that negative sign into a positive sign. Or if you wanted to, if you like this way of writing it better, you could say it equals 4 minus, put a parentheses around this, right? So now you do this stuff. So that's 6, keep the minus, and now 2 times 8 is 16, right? So that is correct. But as you can see, if we want to subtract this, right, and we saw the that subtraction doesn't have that associative property, right, where the grouping doesn't matter. The grouping does matter, and the reason is because if we want to take out these parentheses, right, then this negative right down here is going to turn this other negative into a plus, right? It has that minus sign out in front is really like it's multiplying this entire thing. And so you distribute that negative. So this 6 here becomes, let me switch back to black. That 6 there becomes a negative 6 or a minus 6, right? So think of this as being 4 plus minus 1 times 6 minus 16, right? Think of it like that. You can see the negative sign is multiplying, and we're really just adding that negative, right? And so now you can see more clearly that negative, or that 6 is going to become a negative 6, so it's going to be 4 minus 6. And then this negative 1 is going to multiply by negative 16, which is going to make a positive 16. So we're going to be adding 16. And so this would be the correct answer right here. Well, I mean, I guess you could, actually go through the steps. That would be negative 2 plus 16. So that would be a 14 right there. So that is really tricky with the division, when you're using negative signs in the distributive property. If this is still not making sense to you, because I know it's kind of a hard thing to explain with all these negative signs going around everywhere. If it's still, if you're still not understanding it, just ask me and I will try and do my best to re-explain it in a better way. But hopefully this was, helpful to you, and now you're more comfortable working with the real numbers, how we can add them, subtract them, multiply, divide, what things we can do with addition, what things we can't do with subtraction, division, right? And yeah, so I'll see you in the next video. We're going to start chapter 2 talking about solving linear equations. So that's going to be a lot more algebra, classic algebra kind of stuff that we're going to be going over, and I hope you'll enjoy that.